So they were taught.
I think that anxiety of like the relay is more like
It's all right now.
and just like the equation.
Strokes.
Megan, I was like, this is good to know about like
Yeah,
you like the well, I don't make sure that my daughter is like I
don't want to. This is like.
Hey.
I'm currently in a panic mode. I'm trying to find out.
All right. Hope everyone had a restful break and is refreshed and ready for a lot more dense content now. First up is JB.
Well, I have to really hold it, or can I? Okay. Yeah. All right. Cool.
I'm trying to just turn the light off.
Everyone is ready for the nap?
There's only this one friend. Who wants the lights on? Raise your hand. And then who wants the lights off? Off. Okay. Okay. All right. Let's just don't fall asleep though, please.
All right. So I'm not too sure what was the original title of that presentation, but we talk about the some work that we're doing on for reproducible and sharing of data and also processing of data. And I will of course give you a little bit of my sense and sort of a summary of what I feel is the problem of reproducibility in our field. With a little bit of a emphasis on neuroimaging because I do neuroimaging, but I think those concepts are still general. And one of the driver of the work we do is the feeling that the efficiency of research is really poor. And there was this nice paper recently in the in PNAS showing that the number of papers and articles that are getting out is actually not a good measure of the efficiency of the progress. And they did some pretty nice and interesting analysis on that aspect. But there's so many papers getting out, and one of the reasons, and there are several reasons. I mean, the academic incentive aspect is one of the reasons. The economic incentive aspect of journals is another reason. All those things, for the perfect storm of many articles that may not be of good enough quality to actually go through reproducibility sort of criteria. So the reasons for all those that research that is difficult to reproduce or replicate, I think replication is kind of there's several reasons for that, and I'm going to go through those things and then hopefully try to propose some of those things that we can do now to curb some of the problems. So motivation, so I think you don't have to go back to the reproducibility problem in crisis. We can describe that in a fairly good way already. The one paper that I would still emphasize that you may want to look at is actually is the why most public research findings are false. It's more like a statistical argument of the and it's it's kind of a 2005 paper. And you see when are we today? Like exactly 20 years ago later, things haven't changed dramatically or fundamentally. And I think that's, we have to ask ourselves why that's the case. And I think, again, the culture of research is the thing that is probably a motivation for that. There was a good NIH plan for improving reproducibility. I think it has moved the post a little bit. I mean, there's a lot more data sharing aspect. Now, how is that data sharing is done and is still a problem often, but I think there was a good plan at that stage, and hopefully if NIH doesn't fall down more, there's still going to be push in that direction, for the so what's the gap analysis? I would divide that gap into two big areas. One is the analytical flexibility problem. How many people have seen that paper before? Just to have a sense, it's called it's the Botanic laser paper, 5 years ago. Only two people. So let me describe that quickly. The paper is about a neuroimaging data set that was sent to 70 different labs, and they were very precise instruction and documentation of what the data set is about. And that neuroimaging data set was analyzed by those 70 labs independently. And then the question was, hey, hypothesis one, is that condition greater than that condition? Can you do the, can we exclude the null hypothesis for that or not, and so on. And what you see here is, do I have a mouse? Yeah, yeah. No, we can't see the mouse on the screen. Oh, yeah, you do. Okay. So what you see here is like the 70 times 70 labs correlation of the images that are kind of so you see that there's a big cluster of labs that found correlated images. So that, for instance, condition 1 versus condition 2, those images of the brain were fairly correlated. Okay. And then there's a bunch of labs here that are anti-correlated. Okay, so about 10 of those labs, so 50 of those labs find things that are correlated, 10 of those labs find things that are anti-correlated, and then there are another 10 labs that find things that are not correlated, or not anti or not correlated, it's just like uncorrelated. And then if you look at first of all, if you look at those that red area, you think, okay, that's great, so many consensus. But then if you look at the correlation coefficient between those things, they're not great correlation coefficient. They're not. And then if you look at the hypothesis testing aspect, even if the labs that are kind of showing the consensus in some ways or correlation of their brain images, even in that situation, there was about 50% or 40% of the labs said yes, so we can reject the null hypothesis, and 60% said no, we can't reject. So almost 50-50. So almost random, almost random aspect of whether we can reject that hypothesis or not. Yeah. So that is very, very, very concerning. And one of the things that is the problem is really like every lab would do different pipelines and different things, and it's unclear what is the right way of doing it. So there is some consensus, but it's as soon as you start to do the null hypothesis testing problem, then you go to the random thing. So can you imagine that happening now in the literature? Okay, that's one of the problems. And this was like, a neuroimaging bold data set. This is the same experiment almost done with like diffusion and tracking. So like, can we give the same diffusion data to actually 40 labs in that example and give us back the results and let's say how they resemble. And again, in that situation, there's a very wide analytical flexibility problem. As part of this is some work from my own lab on the same sort of things for segmentation of the brain, cortical thickness measures and all those things, showing that with different segmentation and cortical thickness assessment, you have like very little same sort of correlation between brain regions across subjects. So in all those neuroimaging sort of aspects, we have like an analytical flexibility that is fairly problematic. The second, and I should time myself because last time I think I went to a third of the slide. And how much now? So the second big aspect, so analytical flexibility is one of the big problems. Okay, let's think of it. Second big aspect is for replication or for replication aspect or generalization aspect. this is an experiment that took some of the UK Biobank data and learned if the subjects were, let's say, smoking or having like a risk for disease or something like the different things, but like let's learn about a potential outcome using subpopulation in the UK biobank. So we learned that potential outcome from the young subjects, for instance, and we try to see whether that learner has good prediction value on the older subject, for instance, or male, female, or whatever. And the answer is in that case, there's very, you degrade the performance of the learning very quickly if you change that subpopulation, which means that if you really want to have a proper sort of a prediction on a general population, you need to learn from very, very large different populations. And that is the problem. There is also more like a classical standard, like Keith can talk a lot about that easily problem, which is the sample size problem. It sounds stupid at that stage, that there is a sample size problem. It's still a problem. I love that picture. It's a very old picture. It doesn't really matter. It's showing that the relation between BDNF and the hippocampus volume with a smaller cohort and early publication. So the x-axis is the publication time, and the y-axis is the effect size of the correlation between the BDNF and hippocampal volume. And you see like a small sample size would give you some very variable sort of effect size, and then as soon as you start to increase the sample size with like bigger cohort at the end of the later in the time, then the effect size goes down and to a point where the effect size is almost zero, and we don't know whether there's an actual effect. But the interesting aspect is all those publications that were kind of a bit with high effect sizes and small sample size problem, and that does go to the publication in the literature because those are significant. And there's a very interesting and sort of like this is the work that shows that the same sort of effect happens as well, or this kind of the overfitting sort of kind of effect happens as well. When you have small sample size and you do some prediction of disease, for instance, you're trying to predict the disease. That prediction, for instance, some psychiatric disorder or Alzheimer or depression and so on, and that prediction is getting worse if you increase the sample size. So the kind of the effect size, which is here the accuracy, the reported accuracy of the prediction of the diagnosis from neuroimaging features, that is going down if you have a larger cohort. And the reason is that basically the test and validation and all those things, it's kind of like it's like a p-hacking aspect of the learning aspect in those factors. That's why this is happening. Everyone has heard about p-hacking? Yes? No? Okay. So it's a like I would say cross-validation hacking or machine learning hacking. Yeah. And if you do try to embark in actually trying to replicate things that are, so this is a large project that I was involved with, which is, how do we replicate biomarkers from, T1 images for Parkinson's disease, for instance, in this Parkinson's disease. We looked at a review paper that had 11 articles that were like, in that category that were using T1 for like, prediction or analysis of PD data. And in those 11 things, we found out that, first of all, finding again the cohort that went into the paper was super, super hard. And therefore, a lot of the things we couldn't replicate just at that level. Then the analysis pipeline was also another super hard aspect, which we couldn't replicate in many cases. Statistical analysis was more mixed. Like, there was sometimes when it's a simple, like, ANOVA or things like that, that's easier to replicate. That's like when things are clearer. And then, machine learning was also very difficult to replicate because, like exactly what model, what kind of the cross-validation aspect was done. It was complicated. So that is just a real experience of putting 2 years of work with like many students trying to replicate all those things, and mostly the answer is that doesn't replicate well. Last thing on that side of things a bit is the if you think of the p-hacking problem, please think of a pre-registration. That is really the tool to curb p-hacking. And I think that works also for other things like machine learning hacking. So that's just one example that we had, like kind of a smallish data set, and because data sets are data set, like we can't where we do that registration and also use tools to actually have a very large cohort for controls to make. So eventually, the problem is like how do you find that what is true from the literature, and that is like a meta-analysis kind of problem. That problem is compounded by the fact that if you look at that distribution of z-value in the literature, you see that there's a little gap in the middle. And what does it mean? It means that either people in their paper don't report those values, or the more problematic case is that often the paper themselves are not going into the literature because they're not significant. And if they're not significant, so whatever analysis of meta-analysis you do, analysis of effect size you do in the literature, think of all the papers that have not been published because their effect size were not enough. And therefore, you are super overestimating your effect sizes in the literature. That is a fact. And how much, it's a problem is to know, it's difficult to know, but that's the fact. So summary, literature is growing very fast. It's very hard to reproduce in many cases. Analytical variability is one thing. Sample size, the subset shift, all those problems is in another, like so in the big picture, two big things to take care about. And a lot of those problems would be, at least the second part would be like, curve if we could extract from the silo data set many more data sets. And and many of the data are still dark data, which means that they don't leave the labs or the clinical research environment where they are acquired. So the thing that we worked on is to try to see if we can develop infrastructure and tools to kind of help those two problems. And how do we do that? And how can we use those things today? One word of the kind of trying to develop those things, developing an infrastructure, developing a tool that, we hope like a large population, researcher population will use, comes with caveats. And the big caveat, I think, is, one of the big caveats is like, you need to have like, solid software development implementation. And that's not given to any lab and it's a skill or, expertise to acquire, and that's not, very common to like many labs. There's a second thing, which is how do we sustain those things? And the more I think about it, and the more it cannot be sustained by one lab. I think that's the problem is that the academic incentive is pushing us to do your own thing, and to some extent, there's no choice of doing that. But the real kind of a global optimization incentive would be, let's get together to build those things such that we have a way of sustaining across many labs those efforts. So that also goes with the governance aspects. So if I am the one that deciding on those development of those things, that's not like again, that's not something that can scale in some way. So we need to find the right governance of those projects, that is like community governance. And I think that's also an opportunity to actually build those communities and standards. I think Repro Rehab is one of the places where you build a community, and therefore you build also a community of practice and good practices. And I think that's one opportunity in that direction. So fair ecosystems, I'll talk about two projects that we are developing in the lab, and with overlaps now, which is really a cool thing to see happening. It's starting. I also should say that's also like a kind of a child of a reproning. Those projects are a child of reproning. They were influenced a lot by the reproning sort of P41 project, and you know, yeah. So one of the key things that I think should happen in the future is to move from the current paradigm in terms of data set aspect, from the large centralized where like you have to either be on a RAP and do your things on a RAP, or you have to download like a bunch of data where those data have their own like ethical and legal aspects attached to those things. How do we move from that? Because they have like issues with sustainability issues, change are hard on those infrastructures, computation and interoperability are always a problem with those things. The UK biobank is not set in the same way that ABCD is and all those things. So it's going to spend like months at least to actually be able to do conjoint work between different data sets coming from different places. So how do we move that to distributed infrastructure where the data stay local? You are more recognized for the data because that's the kind of stay local. Or I think there's a flexible ethical and legal framework aspect, and it's based on standard. But it has to be based on standard because otherwise everyone will have their own kind of way of organizing and labeling and those things, and that's not going to help us conjointly use all those things. And infrastructure, if you think about infrastructure, there's a nice kind of things of the German trends. I mean, I hope we have German, but they are noticed only when they don't work. And I think that's one thing. They're very hard to change once they've built like the roads and like things like it's super hard to like or train tracks. And they're not competitive space either. Like, it's a difficult thing to say, hey, we've got this big database, and then but there's a better one there. How would we move from one to the other? It's not going to happen very easily at all for different reasons, technical and also governance aspects. Across resources, I think one of the major things that we've been working on for a few years is how do we harmonize things in a distributed manner. So BIT is really our sort of inspiration here. But BIT itself is limited in many ways. It's a wish list really of a recommended metadata. It has some structure, and like for neuroimaging in particular, but and other kind of a data modality as well now. But it's really hard to when you go in the details, then it starts to fail. And I was you were saying yesterday, this morning, I can't remember. And all those things are not harmonized and difficult to, and at some stage we don't know whether that's actually the same variable or not. I mean, age and sex might be easier, but there's plenty of places where a pH 9 or whatever. And this is the top 30 values in a file set content hand, and you see there's right, air, like all those things, and then maybe numbers. Okay, it's a mess. It's a mess, and it's it's very, very hard to reuse those things. So one of the things that we've worked on are really ways of annotating in a standard way your columns or your kind of variables such that those are unique identifier that are recognizable across many data sets. So what's the problem with that? The problem is to actually make a good tool and make a good set of tools that make it easy to do it. Otherwise, it's really hard and people don't and so on. So that tool is actually creating data dictionary that are machine readable. I think the machine readable aspect is really important. So data dictionaries are kind of the first layer. You have to make it for humans. Okay, that's and it is really important. It's the first layer. The next layer is really, can the machine recognize that this is the same variable, and that has to have like a unique identifier and those things. So there's a very nice, maybe I can show you, this is a super cool tool that is called, anyway, so it's a web tool that will, you take your TSV file, then you annotate with like, an ontology and like a terminology that is flat ontology at the moment, those things. And it's also a way of creating a community that shares some vocabulary and terms. So all those things are kind of embedded in that project, in that NeuroBeagle annotation project. This is like the old interface look like. The new interface is much nicer. And what this thing is doing is takes your old kind of a JSON-based JSON data dictionary from beads and then annotates that data dictionary with unique identifiers that say, okay, what age is exactly that variable, and then sex is that variable, and within sex there's what is male, what is female, what is other, what all those things. So that annotation in a kind of a machine readable way is a critical thing that you need to create to make sure that you can then reuse things across many data sets. And I think that's our goal and freedom mission. Then when that is done, we have tools to actually build little kind of metadata databases and ways of saying, okay, now I can have a query across all those things because I know that I have the same annotation on those things. So let me go, I think I have a tab, the query aspect. Yeah, so this tab, can I make it bigger? This is showing you, for the example, the data sets that are on the Austrian Eurocloud system, eBrands, which is a very large repository of data sets in Europe, the INDI, from the CMI Institute, the INDI data sets, some of them, like not all of them are there, of course, but Open Euro in particular, things, and some of our own data sets. Now I'm going to launch and say, okay, I'm going to take all those things and I'm going to say, hey, what are the data set with minimum age of 65, female, and maybe there's no diagnosis, maybe I'm looking for healthy control. And then maybe you have like, a T1 image or diffusion image or something like that. And then I select the query. And that is going to send into a Sparkle query and says, hey, give me back, how many subjects have those things? Okay, what do I get? I get 70 subjects from that data set in Open Euro. I get another data set from Open Euro here, and so on and so on. So that is a way of recreating cohorts of subjects with specific characteristic without moving the data. I mean, at the moment, you just know that those data exist. And then, there's a second layer, which is how do I access those data or not, and that layer is when those data are CC0, then this is a data lab kind of a layer where you can actually sort of retrieve those data easily and work on those. But that's the principle. And it's spreading fast now. I'm happy to see, and it's also demanding in some ways, but it's spreading fast and it works very well. Yeah, this is some of the nodes now. There are many more, in there. Especially one of the projects that we worked very well with is the Enigma PD project, because Lab is working on PD quite a bit. And Enigma had really that need of knowing where is what and how much subject and how much things. One thing that didn't emphasize is that you can actually also search for are those things being processed with a specific pipeline or not, and something. Transition, yeah, how many? Is it already time? Okay, I'm finished almost. Give me 30 seconds. The second thing that is interesting is this NIPOPI framework, which is built on the top of a bit study, which you organize your whole study, and then it's a kind of a standard. And then if you have that standard in many places, you can actually much more easily say, hey, now run that pipeline with the new version of FreeSurfer on all the Enigma PD data sets, and those are distributed. But because there is that standardization has been done, and there's a package that uses that standardization, it's actually something as easy as NIPOPI install FreeSurfer version X, and then NIPOPI run FreeSurfer. It's getting before it took maybe 6 months, a year to actually get all those results back because a lack of expertise or expertise are gone or whatever. Now it's something that makes it really possible. Again, it's built on NIPOPI, and you can search for the results this is kind of a dashboard of, you know, in any MapID where who has done what, and there's little tools like that to help. Yeah, I think that's it. The last thing I will finish with is we're using those things to do distributed learning. So actually learning, because we know now what is the organization of the data and how to launch pipeline locally, we can actually do that much easier and then like do distributed learning much more easily. And we also know, okay, this is the age variable, this is the sex variable. And so those two things together enable us to do some pretty easy, I mean, easy, no? I mean, Michelle will help me on saying that because you know, she's actually doing it. It's not that easy, but you know, it's a very much, it's a big step forward to make it, you know, actually learning thing biomarkers across those things in a much more easier way, at least, you know, like, so, and this is like, you know, what, you know, showing that, you know, distributed learning is not, we're not missing that much compared to actually mega analysis where you have to gather all the data together. I think that's it. Take home message. Yes, build communities of practices. I think it's really the thing that I'm more and more interested in some ways. You know, how do we build that community of practices? How do we create the tools that make that those community of practices efficient and good? Yeah. Thank you.